All right. Got a little fan going over here. Hopefully it'll shut off in a second. um, it might be a little extra noisy until it decides to shut off. But it's on a 3D printer, so I can't just turn it off. All right. We're going to do some basically practice on more of the shear and bending diagrams today. So um, I've got, let's see, what do I have here? I've got web work pulled up, so we'll probably pull. I assume there's going to be one in here. I haven't actually checked, but I know that in the past there were some here that I could use, and so we'll probably pull one of these problems that is going to allow us. There's one right there, to draw a shear and bending diagram. And we'll do this a couple of times. We'll do a couple of different things. We'll do some beam stress calculations. We'll do some of these where we have to go in and find the stress at a given point. That's actually what this problem looks like it's going to ask us to do. So today's mostly review of things that we've already done, and we will basically be practicing stuff today, working through some of these problems. Let me check this thing. It is working, but I don't know if that fan is going to decide to shut off or not. If it gets too loud, I'll move the mic, or at least change the direction of the microphone to where it may not be as noticeable, but it's kind of annoying in the background back there. Maybe it'll not be too bad. If it is, let me know, and I'll just shut it off, and we'll restart it somehow. This one I clicked on actually looks like a decent one. It's a relatively simple one, but it looks like a good starting point for us. So why don't we work on this one? Let me copy it. Let's see. Get a copy of it. And let's put it over here. And just do this one. So remember what we've been doing. So the first third of the quarter, we were loading different things, mostly like cables and bars, stuff like that. We were loading them with axial forces, and so that created these axial stresses. Things were trying to stretch and get longer. Maybe they were compressing and getting shorter. Then we finished up that part. It's still part of kind of in the background of things we're doing. We are not in this course going to combine all of our different loadings. So that would be the next course. If you maybe if you're civil engineering or mechanical engineering, you would take another course or several courses after this one, and you would start combining these loadeds. Things would stretch and twist and bend all at the same time. Here we're kind of making them discrete little topics. So right now what we're in the flexing or bending area. And so now instead of axial loads, these what we're calling beams have transverse loads on them. So loads that are making them bend instead of stretch. Now technically, when they bend, part of them does stretch and part of them does compress. Why don't we take a second and make sure that we're on the same page with that. But if we had a beam, oh, is it not going to automatic? Okay, well, not sure. Sometimes it decides to clean them up, and sometimes it doesn't. So if we had a beam, has a point load on it, it's going to be supported. You know, there's a pin and a roller, for instance. And if we're drawing the exaggerated version of this thing, then maybe it's going to bend like this. So if we were to look at the cross section of the beam, or well, not even the cross section, just the side view is fine. But if we were to envision it bending this much, and again, they don't bend this much in the practice, but we're having to exaggerate it so you can mentally see it. In fact, that's one thing that I do whenever I'm trying to figure out kind of how these mechanisms and beams and linkages and whatever the machine might be made of, whenever I try to envision what it's going to do as far as failure goes, I envision it not as metal, but I envision it kind of as a rubbery substance, so it's easy to bend and deform and all of that. Metal is kind of like that, but it's way stiffer, right? Basically, every material is some kind of spring. It just could be that the spring is really, really stiff. And so I usually bring that spring constant way down in my mind to see, well, what would happen if it was going to bend this way. But what the point here is that in this kind of scenario, the bottom of the beam, anything below this dotted line, remember the dotted line that I'm drawing here is kind of a line that shows where the neutral axis would be. Anything below that is going to be being stretched out. So it's actually in tension on the bottom side of the beam, and the top side of the beam is compression. So you still have tension and compression in your beam. It's just you have both of them at the same time in a cross section. So we still have those ideas, but now we're solving a beam bending stress. Remember that equation was this guy. Sigma equals negative m times y over I. M is why we're drawing these shear and bending diagrams, because that m is the internal bending moment. While we're on these little asides here, then let me go ahead and I've been saying that when we draw the internal bending moment and the internal shear force, where there were particular directions, we had to draw the arrows. And we'll actually do some of that in part of this problem later on, but most all the time when I tell you you're writing a equation, summation of moments about some point equals 0, you can choose clockwise or counterclockwise to be positive for that equation. Just like technically you could choose left or right to be positive for x-axis, summation of forces in the x-axis, or the y-axis. You could choose which way is up if you wanted to. In here, so that we all draw the same shear and bending diagrams, we have to have a certain direction for these moments to be positive and a certain direction for them to be negative. So what we have set up in our drawing these shear and bending diagrams is that clockwise external moments. So if I have one like I'm drawing on the free body diagram, if I have an external concentrated moment on the diagram, or if I draw the shear and bending diagram and the picture of the moment diagram, if it's positive, then that's doing a certain thing to the beam. And here's what it is clockwise moments they're the positive ones, and counterclockwise are negative, so they get the negative sign. And it's easy to remember that clockwise moments are positive. So how you remember that is you think about your beam shapes. So you've got the beam could bend this way, or it could bend this way. So it could bend with tension on the bottom and compression on the top, or if you pushed up from the bottom of the beam and made it bow up, then the tension would be on the top and compression would be on the bottom. So you could have either of those. What we're saying is that clockwise moments, so the clockwise moments are the ones that do this, and they're the ones we're going to assign a positive sign to, and counterclockwise moments do this, and we're going to assign them a negative sign when we're reading the shear and bending diagram, or if we're dealing with one of these external concentrated moments on a beam. This one doesn't have one. I just had to draw it on there myself. But if in those cases, we have to assume this direction. And it's easy to remember. So the positive moments, look like that. Negative moments, kind of a frowny face. That's the easiest way to remember it. So which way is tension on the bottom or top and all of that. The clockwise moments or the positive moments make the smiley face, and the negative moments make the frowny face. So that's easy to remember. They told me that, 1993 93, I think, is when they told me. No, 93 or 94, probably 93. And I still remember it. So I think you can remember that also pretty easy. So let's work this problem. So this one is, I didn't even see the number. Let's see if I still have it pulled up. This is problem 12 in optional 2. Also, I saw a thing in the chat that optional 2 in WebWork had closed. I opened it back up. I had it closed too early, so it should still be open. So you can still access those. So this is number 12. And I've got a beam. This is a simply supported beam. It has a pin and a roller. It has a little T-shaped cross-section, so that's different than what we've done. Oh, this is gonna be a So we'll do something with this one. Yeah, we'll do this. There's one part we can't do because we haven't talked about it yet. So maybe that would be something. Let me check if we need to do that today or not. Let's see. No, we'll do that later. So this one's a little bit ahead of its time for us, but we'll just gloss over the part that we can't do. And actually, I won't be able to solve this one in WebWork, so we're just going to do it manually, but that's okay. All right, so we got this simply supported beam. It has a distributed load, and the distributed load is 2,500 newtons per meter. So let's just go ahead and fill in our blanks here. Actually, why don't we we'll just draw our own version here. So let me see if I can make it auto correct the automatic shapes. There we go. All right, let's draw our beam. There we go. Let's put our distributed load on there, something like that. And it said for mine numbers. Now again, you can follow along with this, but you won't be able to put your numbers in WebWork because there's one step that we are going to have to skip over. We've got a reaction at B. It's a roller. The ground that it's rolling on is horizontal, so that makes the reaction vertical. We have a pin at A. Pins have two reactions that are orthogonal to one another. Now this one, I can look at it and tell that AX is 0, so we'll draw it on there, but then we will zero it out. We have some dimensions. Oops, sorry. There we go. So the 2 meters is hard-coded in to the problem. And also there. Looks like I should have drawn that a little bit differently, but it's fine. That is an important point. So on WebWork, in exam problems, you get your own set of numbers and somebody else is going to get a totally different set of numbers. And so the diagrams you get may not be drawn exactly to scale because like I drew here. Now this one I should have drawn better, but maybe these 2 meters are both variable. And the picture looks one way, but it could be that yours are flip-flopped for which one is the longer versus the wider. So don't look too much at the original diagram for scale. You might have to redraw it with your particular set of numbers in there. They're generally not very different from the picture, but it could be. What else do we have? So this one is actually a problem that's set up for us to go to a specific spot. So this little AA with the dotted line between it, that's basically what, whenever I go in there and do something like that, that's what it's saying is that, hey, there's a section that I'm particularly interested in. And this section in this one is 3 meters to the right of the support A, which A is labeled as the pin. So if I were to go over maybe here, let's do it this way. So if I were to go here, and maybe we'll say 3 meters is right there just for convenience. So for some reason, I'm particularly interested in that section. You know, I don't know why, but I am. And so that you could have problems like this. And there's two ways you could go about doing them. You could draw the shear and bending diagram, and that would be totally fine. And you could figure out the reactions AY and BY. Then you could go and draw the shear diagram, integrate it, and draw the bending moment diagram. So you could do all of that, and it would get you to the answer. But the problems that, like this one, that are set up where there's a specific location, 3 meters from the pin, then the better way, and better meaning the faster way. So if it's on an exam, then faster is probably more important. In web work, you know, you've got essentially as much time as you want. So maybe that it doesn't matter so much. But in this case, it is set up to where we're intended to go and create a free body diagram right at that section AA, solve for the bending moment there, plug that into our stress equation. What we're going to do with this is we're going to do that, and we're going to draw the shear and bending diagram. Either one, we at least need to find the reactions. Now for the direct method, we only need one of the reactions because I only need half the beam, so it doesn't matter which one. Looks like the BY would be the easier one, so let's start with that. And we're going to take this and we're going to write summation of moments about point A, because I want to solve for BY. I want to say clockwise is positive. This is when I'm saying you can choose whichever way you want here. For I'm writing my own equation, I can choose clockwise or counterclockwise as positive. It's when I go to read the shear and bending diagram that positive ones have to do a certain thing to the beam for us all to agree on what the shear and bending diagram looks like. All right. So I've got, let's get our purple out because I've been using that as the lumped load. So calculator, here it is. So the little distributed load, whenever you are using a distributed load and you write in the equation, like for finding these reactions, then you usually want to lump the distributed load. This one is 2.5 kilonewtons per meter, and it's 2 meters long, so it's a total of 5 kilonewtons. And it's 1 meter from the pin, right? Because it's in the center of that distributed load. All right, so that will create a 5 kilonewton force with a 1 meter moment arm, and then minus BY times a 4 meter moment arm equals 0. Therefore, BY equals 1.25 kilonewtons. So 5 times 1 divided by 4, the negative sign moves to the other side, becomes positive, so 1.25 kilonewtons. And then I look at this, and that seems reasonable. All of the weight is on the left-hand side of the beam, so the left-hand reaction should be doing more than the right-hand side, so that looks reasonable. So let's just do summation of forces in the Y just to get AY, although if I was doing the direct method, I wouldn't need it. But let's go ahead and get it since I'm going to do both methods. So I've got AY minus 5 kilonewtons plus 1.25 kilonewtons equals 0. Therefore, AY equals 5 minus 1.25, 3.75. Okay, so we have our two reactions, and again, I only need the BY or the AY, which I only need one of them to do the direct method, but since I'm going to do both methods and hopefully get the same answer on both of them, then I I found both reactions. So if I were doing the direct method, which this problem is set up to do, I would now, actually right after I did the By equals 1.25 kilonewtons, I would then cut the beam. Let's get my green out for cutting the beam. I'd cut the beam right at the point of interest, so section AA is what they're talking. It's a little unfortunate that they have pin A and section AA, but typically when you're doing these sections, if you were drawing like a shop drawing or something like that, doing some drafting, then the sections are a lot of times AA, BB, C, they're in alphabetical order. And those kind of drawings wouldn't have pin A on them, really. So normally you wouldn't end up with pin A and section AA on the same drawing, but this is kind of a conglomeration of a couple of different ideas, I guess. So anyway, I would go to that section and cut the beam open, and then I would choose one side or the other to draw. In this case, the right-hand side of my cut looks a whole lot easier to draw than the left-hand side, so I'm going to draw that one. So there it is. I usually draw a little squiggle. Well, I guess it's going to straighten it out for me because I've got the auto shapes on. Then I've got By, which I would have just solved for. I've got a distance of, that would be 1 meter, right? And then I've got my internal shear, which I have a direction I have to draw. I have to draw it up. An internal bending moment, which I have to draw it this way. And that's dependent on which free body diagram side I'm drawing. Just to be 100% sure, you wouldn't do this to solve the problem, but just to be 100% sure, let's draw the other half of the free body diagram, just so we are absolutely certain how these would look. So the other half would be this guy, and I would have the AY, which would be 3.75 kilonewtons. I would have the distributed load. I could draw the distributed load, or I could just draw the lumped version of it. I think I will put the lumped version on here. Maybe to keep with my theme, though, I will draw it in purple just to remind myself that it's the lumped load. I think it probably is a good idea to do multicolor drawings when you can. I actually, maybe I'll find it and post a link to it. There's a really good pen that, you've got the little multicolor pens that you get when you're, in elementary school or whatever, and those will work, but there's actually a good version of that. I'll have to find it on Amazon. It's not terribly expensive, but it has the 4 colors and a pencil. It has a pencil in there too. So it's actually really good for this without having to have a whole set of pens to draw. But I think, at least for me, it does help to have multicolor drawings where the black lines are always your object lines, the red are always your forces, the blue, I usually use blue for dimensions, and then the green are axes and other notation type stuff, like the free body diagram cut lines and stuff like that. It usually, I think, helps with the problem process. I started doing that a long time ago, and I still do it, and I think it probably will help. Just make sure, if everything's all pencil or everything's all like blue ink or whatever, then some of these things get lost and you end up confusing object lines with forces and all that. I think the color helps. I'll find the link to that little pen that's pretty good, or get whatever you want. But I think it does help. All right, let's see. Back to this. I would have to draw my internal shear force here on this part. It would have to go down, and the bending moment would have to go this way. And so I could use well, and then technically I'd have some dimensions on there, right? I'd have the let's see, let's do them this way. Got 1 meter there, and that distance is 2 meters. Okay. So either one would work. Either one of these free body diagrams. Typically, I try to find the one that has, the less to draw. So the right hand side has slightly less to draw. So that's the one I would actually work on most of the time, is this one. So let's get it and work on it. There we go. There we go. All right, so I would have drawn this. And then if the problem is actually asking me to solve for stress on top and bottom of the beam, why don't you take 5 seconds and mentally think about why you would do top or bottom of the beam. Why does it matter? All right, so sometimes it doesn't matter, first of all. When it does matter is when you have a beam that is like a T, or it doesn't have a horizontal line of symmetry. So let's look at our little T cross section up here. Maybe we'll temporarily draw it over here. We'll have to move it because this is where our diagram's going to go, but let's take and think about our T shape. So this beam, apparently, I haven't been drawing the little T flange on here, but it has a T cross section. And if we remember well, I drew it. Oh, I erased it already. When I drew the little dotted line for it deflecting, I said that dotted line was at the neutral axis. The neutral axis is at the centroid of the cross section. So if this T shape is my cross section, then the neutral axis is, somewhere up here. We're not going to find the exact location right now, but somewhere up there. And everything below that neutral axis, so down here, is in this case in tension, and everything above the neutral axis is in the other. So in this case, everything in red is in compression, everything in blue is in tension. Sometimes it's flipped if your beam is humping upwards versus bending downwards. Most of the time the beams are bending downwards, but you could have beams that have loads pushing up on them. So that's one reason it matters, is because it could be tension or compression. And most materials don't care about that until you get into civil engineering and these beams are concrete, and concrete behaves very differently in tension versus compression. So then it really matters. But for ductile metals, like what we're going to deal with in this class, it doesn't really matter as far as the strength goes. But also, remember in our equation, sigma equals negative m times y over I. That distance y is the distance from the neutral axis to the point of interest. So it's either this distance, or it could be this distance. And the one that goes to the bottom of the beam is a larger value than the one that goes to the top of the beam. And so you have different bending stresses. The magnitude for sigma is different because you have the same moment. You have the same moment of inertia. I is moment of inertia if you don't remember that. But you have different, I even know the name for y. But the distance from the neutral axis, you have different distances. So it's sort of like a moment arm, but it's not really, but it's sort of like that. But you have different values for that value of y, and you will have different magnitudes of stress. Not just different signs of stress, tension and compression, but actual different magnitudes. So that's why this particular problem is asking you to do both the tension, it doesn't tell you tension and compression, it says top and bottom of the beam. Now, all of that, what we really have to do to solve this is we go back to our little free body diagram, and now that we've got our little free body diagram with the M and V and the 1.25 and the 1 meter, we just go and do summation of moments about I usually do the cut. That's usually the best place to do for these little beams. I'll do, in here again, I'm writing my own equation, so I can do clockwise positive if I want to. Equals 0. So it just says V, the cut is this point here, right there, right there. So V does not create, and I know I've drawn it a little offset from that, but it's on that surface. I just didn't want to draw it on the surface. So V is does not create a moment about the cut. M is a moment, so it creates a moment of M. So M, I have drawn M going clockwise. I said clockwise is positive, so it gets a positive sign on M. Minus 1.25 kilonewtons, and that does have a moment arm of 1 meter. Therefore, M equals 1.25 times 1, 1.25 kilonewton meters. And that's not the answer to this problem, but that is the internal bending moment. Now, it actually wants the stress, so we'd have to take and plug M into our equation down here. We'd have to get Y from the cross-section of the beam, which means we have to find the centroid of the beam. We can do all of that part, but I, the moment of inertia for that T-shape, this is not a standard T-shape that we would go look in our charts, WT, 4 by, whatever. It's not that. So I would have to go and show you how to do the moment of inertia. We're going to do that Thursday. I think that's Thursday's topic. We will get to that, and maybe we'll come back to this problem, but we can't actually do any more than that for now. We would have to do a little more lecturing to be able to do that. What we can do, though, is now we can do the same thing, but draw the shear and bending diagram. So I've already found AY and BY. I never wrote AY, though. AY is 3.75 kilonewtons. I'll draw my little guidelines here. Whoops. I wanted to draw a straight line. There we go. Can't figure out how it wants the line to... Oh, shift first and then draw. Okay, there we go. So there's some guidelines. There's only the two ends and the end of the distributed load. I could draw one here, because that's where I am interested in. This particular problem says I'm interested in. It may not be the maximum moment, but that's not what this problem is asking us to do. Let's draw our horizontal. Well, that didn't do. There we go. That's our reference for V equals 0. Now it's wanting to correct everything. Kilonewtons. So let's draw, what color? Oh, this green looks nice. So we start at 0. Let's get my calculator. Oh, I need an idea of, let's see, I'm going to go up to 3. All right, so these will be, it'll be a little crowded, but we'll do 1, 2, 3, 4. Right? So we start at 0, instantly get to AY, which is 3.75, so that's, right here. And then we have a distributed load. The distributed load is a total of 5 kilonewtons. I am currently at 3.75. I'm going to lose because the 5 is pointing down, so minus 5 is negative 1.25. So that would be that'd be right there. It is a constant distributed load. It's evenly distributed, so that means that I have a constant slope. Just to make sure, so an unevenly non-constant shear load would be something like this, right, where it has a constantly changing value for shear. In that case, my slope would be constantly changing in the shear diagram. So this one is just a solid 2.5 kilonewtons per meter. It doesn't vary up or down. So that gives me a constant value, which is a constant slope on the shear. So I just have a straight line from here down to here. Okay, and then nothing happens until I get to by, which be there. By happens to be a positive 1.25. I'm at negative 1.25, so I go up to 0. Okay. So there is my shear diagram for the entire beam. So I know that the maximum shear occurs right at the pin at A. So if I need to check for shear failure, that's where I would check. Now what I need to do is I need to go in and integrate the shear diagram, which means to me I need to calculate the area of all the little shapes. So the first one is this triangle, which I don't know the base of. So I do have to go figure out what's the base here. And that distance, to get that, I take the height of that triangle, 3.75, and I divide by the slope of that line, which is 2.5 kilonewtons per meter. So 3.75 divided by 2.5, 1.5. So it says that it takes 1.5 meters under that distributed load of 2.5 kilonewtons per meter to go from 3.75 where I started the triangle down to 0. So now I have the base and height of that triangle. I can calculate this area. 3.75 times 1.5 divided by 2 because it's a triangle. All right, so it's going to round a little bit, so we'll deal with it. 2.8125. I will keep all those decimals. This one must be 0.5 meters. And this area, let's see, we'll put it kind of around there. It has a height of negative 1.25, a base of 0.5, and a triangle, so divide by 2. Negative 0.3125. That would be, those units are kilonewton meters. I'm multiplying a height of kilonewtons, a base of meters, so the area is kilonewton meters. This rectangle, I believe I will divide it into 2. So normally you would not do this part, but I actually want to know the height at that section line that I drew, the dotted line. So that's why I'm going to treat this as 2 separate triangles, just so I get that height in my moment diagram directly without having to kind of figure it out. So this is, let's see, I have to make sure I have my units correct here. Or not my units, my dimensions. Those are both 1 meter. That's 1 meter. And that's 1 meter. Even though I didn't draw it perfectly even, that's what it is. So this is minus 1.25 meters, kilonewton meters. And so is this one. Okay. Hopefully all of that is correct. Although something seems a little off, but no, I think it's right. All right, let's draw our reference line for the bending moment. Moment equals 0. These units will be kilonewton meters. It also starts at 0. Now this one would probably do good again to have some reference there. I drew this little reference line because that's where this shear goes from positive to negative, where it crosses the 0 shear axis, and that's going to be a peak in my moment diagram. I'm going to go up to that, and then it's going to start becoming negative, so it'll go down again. So start at 0, I go up 2.8125. That's the area of the first triangle. Oh wait, I'm writing it in my calculator so I can use it later. 2.8125. We'll make, that should be the peak. So let's count by 1, 2, 3. So it'll go up to 2.8. It'll go right up in there somewhere. Now, this is a constantly changing shear force. It starts out a large number and it goes to 0. That means the slope in the moment diagram Starts out steep, large number, and then goes to 0, which is horizontal. So it's going to do something like that. That may be exaggerated, but it's something like that shape. And then we've hit our peak. Now all the rest of the shear diagram is negative, so these are all going to make it drop down. So I am at 2.8125. I'm going to subtract off 0.3125. Gets down to 2.5, so right there. Also curved, but you know, there's not much to it. Then I subtract off another 1.25. Gets me to 1.25, which would be right there. This is a constant shear, so it's a constant slope. And then I'm at 1.25. I should be writing my numbers here. Let's see, that one was, I don't remember. Well, we'll have to figure them out. And then another minus 1.25. Those should be the same slope because they are the same value of shear, but since I drew it a little bit off, they look like they're different slopes. But here is the shear, or well, the bending moment at my section AA. You know, this line represents section AA, and I can just see that it's 1.25. The units are kilonewton meters, which is the same as what I got over here. It is not the maximum moment in the beam. The maximum moment is that peak over here, which was 2.8125 was the actual maximum. So all of this is the shear, is the bending moment anywhere in the beam. Got some crazy lines in there. So that is a way to do that. If you have a problem that is asking you for, hey, what's the bending moment or the shear stress or the flexural stress, you know, one of those kind of things at this point, then the better process is what we did first, versus drawing the whole shear and bending diagram. Because it could be, even if you could always get it right with a shear and bending diagram, but it could be that you know, that point is right here, and that's kind of hard to figure out. Well, you know, what is that point's value? Because now I've got this curve, and I have to figure out the actual equation. I would have to go, you know, integrate the area up to that point and figure out some more stuff than I'd necessarily have to if I just do the direct process like what we did at the beginning. All right. All right. So that was a relatively simple shear and bending diagram, but I wanted to use it to make sure that we still knew how to do the direct method. Let's go find a little bit better problem to work here. Nope, we've been logged out. Oh, all right, so these are definitely set up for doing the moment of inertia, which is not what we're working on right now. Well, that one's pretty simple. So this is a cantilever beam. We haven't done a lot of cantilever beam stuff before. This problem is another one where you could go and draw the shear and bending diagram, but it's asking for the maximum tensile flexural stress. Know that for a cantilever beam, the maximum stress is at the wall, or the floor, or the support, wherever the support is, floor, wall, ceiling, some angle somewhere. It's at that fixed support is where the maximum flexural stress will be. Well, these are not particularly interesting problems. Let's keep scrolling and see if we find a good one. I don't want one that's unnecessarily difficult, but we may just have to make up our own. These are all about finding the moment of inertia. Oh, well, all right. So that one is a lot. We could do that. Let's see if, oh, that's the last one. Let's just make our own. We could do this one, but it's a little unnecessarily complicated, but we could handle all of these things. Let's just do our own problem. Actually, let's look and see for a second if that pin is easy to find on Amazon. Actually, Amazon's not coming up, so maybe it's not. There it goes. I think it's a 5-color